Okay. All right. Oh, yeah. All right. So today is subspaces of Rn. All right. The section focuses on important sets of vectors called Rn in Rn called subspaces. They provide useful information about the equation ax equal to b. Okay, so a subspace is any subset of Rn that has the zero vector, is closed under addition and closed under scalar multiplication. So that's the definition of a subspace. So it's a very simple definition. Then they give you an example. And then the proof. The proof is, again, just a normal linearity proof. Here's another example. We have some line that doesn't go through the origin. We can easily see that it's not a subspace because first, it doesn't contain 0, but also because for any 2 points on the line, their vector addition is not in there. So therefore, it's not closed under addition. It's not a subspace. All right, then they give you another example. Let's see. For p vectors in Rn, the set of all linear combinations is a subspace. Okay, so yeah, so they give us some terminology that we can refer to the span of those p vectors as the subspace spanned or generated by those vectors. So basically, for any set of vectors, there is a subspace equivalent to the span of those vectors. Because it's all linear combinations. So 0 is obviously in it because you take the coefficients all equal to 0. It's closed under addition because linear combination, it just is. And then scalar multiplication, same thing. The definition of linear combination gives us that scalar multiplication. Note that Rn is a subspace of itself because of the three properties. Yeah, okay, great. And another special subspace is the 0 subspace. 0 because 0 plus 0 is still 0. And then any c in R times 0 is also 0. Okay, so, all right, some more definitions. The column space is just all linear combinations of the columns of the matrix A. So, yeah, pretty easy definition. It's the same as span. Call A just equals span calls A. So, whatever. The column space of an m by n matrix is a subspace of Rm. Yeah, that's just because you take the linearly independent set of the columns and then it's basically deduplicating, and then you can get the dimension. So that's fine. Determine whether or not B is in the column space of A. That literally just means, does there exist a solution to AX equal B? So that's not that. We don't need to walk through that. All right, the null space. This is a cool definition. I actually like this definition. So the null space of a matrix is basically the set of vectors that equal 0. Now we know that if the columns of A are linearly independent, then the null space is just the 0 vector. And so it turns out that, and the reason why this is cool is that the null space, and some people call it the kernel of this linear transformation, is a subspace. So it's a vector space itself. When A has n columns, the solution of solutions of ax equal to 0 belong to Rn, and the null space of A is a subset of Rn, and null A has the properties of a subspace. So they're probably going to prove that. The null space of an n by n matrix A is a subspace. Equivalently, the set of all solutions of a system Ax equal to B of M homogeneous linear equations in n unknowns is a subspace of Rn. That's just saying what we just said. But the proof is probably pretty interesting. So or I'll write null, but I prefer the word kernel just because it sounds cooler. But null space is probably a better idea of what it actually is. Kernel, I don't know. Let's see. Kernel. Linear. So Wikipedia calls it the kernel. But what's the history of the name? I don't know why they call it that. But in any case, okay, so null A is the set of X such that AX equal to 0. Is that true? The set of all solutions. It's actually really cool that it makes a... So the proof that null A is a subspace. So the first thing is, 1, show 0 is an element of null A. So that's easy because A times 0 is equal to 0 for all A. So it really doesn't matter. So we have the 0 vector. Now we want to show, suppose AX equal to 0 is equal to AY. Then we want to show that it's closed under addition. So these are for any X and Y in the null space. We want to show that X plus Y is also in null of A. So we'll just write A of X plus Y, and then directly by linearity we get A, that's equivalent to A times X plus A times Y. And we know that these are both 0 because we assume them to be in the null space. Therefore, it's closed under addition. This is why I feel like linear algebra is just the least surprising branch of math, because it's like it always just comes back to just apply the definition of linearity. Okay, so now we want to show that, we'll just do this. A times AX, little AX plus BY. So now we have scalar multiples of these things. And we assume that, it's just going to be A times big A times X, which is A times 0, which is equal to 0. So therefore, it is a subspace. So this is like a pretty immediate proof. You just get A plus U is equal to, so apply linearity. And then here you can move the scalar out. And we're good. Okay, here we go. This is an important definition as well. So the definition of basis. A subspace typically contains an infinite number of vectors. Some problems involving a subspace are handled best by working with a small finite set of vectors that span the subspace. The smaller the set, the better. It can be shown that the smallest possible spanning set must be linearly independent. So a basis of some vector space is defined as, it doesn't even need to be a subspace. I think it's defined just for vector spaces in general, is some linearly independent set in V such that span of V's is equal to V. Okay, or H equal to H, whatever, however you want to say it. And then the standard basis is obviously just the one we're all used to. That's not very complicated. Find a basis for the null space. Okay, that's kind of an interesting problem. I like this problem. Shows that the standard procedure for writing the solution set of ax equal to 0 in parametric vector form actually identifies a basis for null A. Okay, this is a cool problem. Okay, we put the augmented, we find the, okay, we reduce A to echelon form for the augmented system, and we get x1 minus 2x2 minus x4 plus 3x5 is equal to 0. Okay, let's just go through writing. Okay. Okay, so then you move everything but the echelons into the right hand side. We're gonna get um all right, I'm gonna do this one. So suppose that we have x1 minus 2x2 minus x4 plus 3x5 is equal to 0. x3 plus 2x4 minus 2x5 is equal to 0. And 0 equals 0. So we're going to have x1 is equal to 2x2 plus x4 minus 3x5. So then yeah, I totally forgot about this. So then in this one, so okay, so I guess the thing that's important is that x1 and x3 are not free. So that means that we can write x2 times, I don't know why this is a 2 here. Oh yeah, I remember. Okay. It becomes 2 1 0 0 0. Because if x1 equals 2x2, then whatever x2 is, you multiply that by 2 to get x1. All right, that's easy. All right, so this all makes sense, right? We for this one, yeah. So there's a 1 for x4, minus 2 here, and a 1 here. So that's what this is going to be. Okay, so let's write down, I'm going to write it out. All right, so x2 is going to be 2 1 0 0 0 plus x4 1 0 minus 2 1 0 plus x5, which is that's going to be minus 3 0 2 0 1. Okay, so that's the parametric vector form. Thank you. Thank you. Do you want a LaCroix or something? I think we have ice. Okay. I might get one in a minute. All right. So I guess the punchline of this is that this is the basis for the subspace. Yes, yes. This is the basis because any linear combination of these vectors should equal 0. Is that okay? In fact, this construction of u, v, and w automatically makes them linearly independent because equation 1 shows that 0 equals the linear combination if and only if the weights of the free variables are all 0. Right, so that shows that these are linearly independent. But then in what sense does this okay. Oh, what it is that okay, for any linear combination of the vectors, you're going to get a set of 5 numbers that if you multiply that vector by a, then you'll get 0. Okay, that's what it means that this generates the null space. So these are independent, and you can't find numbers x2, x4, and x5 such that this sum becomes 0 unless x2, x4, and x5 are all 0. Okay, that was actually a good review. So u, v, and w are a basis for the null space of A. All right, now finding a basis for the column space of A is actually less work than finding the basis for the null space. However, the method requires some explanation. Let's go. Okay. Find a basis for the column space. I mean, it's already in echelon form. It's clearly just going to be note that B3. Okay. The fact that B3 and B4 are combinations of the pivot columns means that any combination of B1 through B5 is actually just a combination of B1, B2, and B5. Oh, okay. So that's what you do. You write it out as a linear combination, and then you rewrite the dependent columns as linear combinations of the independent set. That's pretty cool. Because their columns form an identity matrix. Okay. So the pivot columns form a basis. But I guess the basis, interestingly, we can see that this last one is free. The matrix B in example 7 is reduced echelon. The hint or general matrix, recall that linear dependence relations among the columns can be expressed. Oh, that's wild. The pivot columns of A form a basis for the column space. However, the pivot columns of A, you have to use the pivot columns of A, because if you use the echelon form B, like, see here we have 1, 0, 1, and 0, 0, 1, and the last is all 0. If we use those, we're not going to, it's not the same set of points that you can reach. So the columns of an echelon form B are often not in the column space of A. Interesting. Okay. So now let's do the practice problems. So is U in null A, is U in call A? So let's just do it in code, because it's not worth doing it by hand. Okay. So we have A and U. So to check U in null of A, we do, yeah, just A times U. And if it's equal to 0, then we're good. Okay, so then yes. So it's in the null space. Now we want to check U in call A. Then we want to do A backslash U, because that means that there's some linear combination X. So it's not, so no. Test throws. Okay. So no, it's not in the column space, but it is in the null space. And we should note, I'm pretty sure, well, first off, 0 is always in the column space and it's always in the null space. So it's not, you know, you might think that the null space and the column space are disjoint, but that's not true. All right, find a vector in null A and a vector in call A. All right, so null A, let's just take the 0 vector. we're lame like that. Take something easy. A times 0, 0, 0 is just 0. And then something in the column space. Let's just take 1, 1, 0. All right, suppose A is invertible. What can you say about the column space and the null space? Okay, so the null space. So if it's A is invertible, then the column space is Rn. It spans Rn. And the null space is only the 0 vector. All right, let's see if we were right. Okay, so the first one is it is in the null space. It's not in the column space, so we were right about that. Then here, finding a vector in null A requires more work than testing whether a specified vector is. However, since A is already in reduced echelon form, the wait, did it ask for a basis? It just says find a vector in null A. Oh, here's an interesting statement. Okay. Oh, that's interesting. Okay, yeah, I see what they're saying. In this particular case, the same vector v is both in null A and col A. So here's an example of a non-zero vector that's in both of them. For most n by n matrices, the 0 vector is the only vector in both of them. So that's interesting, actually. All right, and then the last one, if A is invertible, then the columns of A span Rn, like what I said. The columns of A... Okay, so the column space is all of Rn. Okay, that's great. Since A is invertible, the equation only has the trivial solution. This means the null space is just the 0 vector. Okay, great. So we got all those right. Now, since this is more of a theoretical section, we'll probably do the true falses. And I don't know what else we're going to do. Let's just read through them. Give a specific reason why this set is not a subspace. Find two vectors. Okay, I mean, this is obvious, right? Take like 1, 0 and multiply it by -1. Scalar multiplication is not closed, so that's easy. Here we go. We're going to take 1, 0 and 0 minus 1. Clearly, it's not closed. Take 1, 0, multiply it by 2. Not closed. Take 1, 0 times -1. Not closed. Okay, so those four are just like obvious. So, okay. Oh. All right. Determine if W is in the subspace of R3 generated by V1 and V2. Okay, so wait, hold on. That's a good problem. So we have V1 is equal to 2, 3, minus 5. And V2 is equal to -4, -5, and 8. I mean, asking whether or not it's in the subspace is is just a matter of reducing its augmented, right? Okay, so let's do that. All right, so wait, this is inconsistent. So that means that no W not in span of V1, V2. Okay. All right. So I'm just gonna say wait, why would it write it like this? There we go. I'm gonna say no. Yeah, so no. Even though we have like a free variable here, we haven't um oh yeah. Oh. No. Oh yeah.
Like I don't know, a baby.
All right, let's do this next one. How many vectors are in V1? There's 3 vectors in that. How many vectors in the column space? Infinite. Right? No matter what, it's going to be, well, unless the column space is 0, like just the 0 vector, then it's infinite because you could just take an infinite number of scalar multiples. Is P in it? All right, let's get the Julian then. I don't know why it keeps doing this. I just want the normal one. Ugh, that's so annoying. Okay, whatever. Yeah, so this is in the because we're gonna get x1 is equal to minus 7/4 x3 plus 2.25, and then x2 is equal to minus 2.5 x3. Actually, I think it's supposed to be minus 3.5. So and then x3 is free. So the parametric vector form of this thing is going to be minus 2.5 minus 3.5 plus, oh, and then what? And then 0, I think. and it's going to be x3 times minus 7/4 minus 2.5 and 1. Just double check that we got it right. What? Actually, wait. That's right. That's right. That's right. And that's right. And that's right. Okay, so I got it right. Never mind. That's correct. All right. So the answer is okay, then did I give it the whole thing? So okay, just to recap, my answers are there are 3 vectors in v1, v2, v3. Then since the since if we take r ref of a, we have we don't get the 0 vector. So it's going to be infinite. Uncountably infinite if we're being cringe. And then is P in the column space? Yes, it is. There's 3 infinite, and then yes, because oh yeah, you could just take x3 to be 0. That's the easiest thing. Yeah, and then this is just as a linear combination. All right, that's easy. Easy enough. So 7 is done. 8. Do we want to keep doing these? I mean, these are boring, right? With u equal to the determine if a u is in null u. I mean, it's literally just a matter of calling backslash. Or no, not calling backslash, calling a times u. All right, in exercise 11 and 12, give integers p and q such that null a is a subspace of Rp and call a is a subspace of Rq. Well, the biggest dimension that the biggest possible dimension that call a could be is R3. So I would say that. So let's see. Well, no, but I might. I mean, the thing is, like, for differential equations, a lot of it, more of it is writing. This one is more just talking because they're so obvious. Like I said, linear algebra is unsurprising. Does anything surprising happen in linear algebra? I don't know. These kids, man, they go crazy. Running around, throw a water balloon. Okay. So, Okay, so for 11, I would say call A is a subspace of R3, and the null space is R4. It's basically just a question about the domain or the codomain. Yeah, these are good problems. Actually, 11 and 12 are good because they make you realize that that the column space and the null space. Yes, that's what I said. Okay, 4 and 3. All right, so for this one, it's going to be the column space is in R4 and the null space is in R3. I'm not doing that. I'm not doing that either. Determine which exercises, which they're building a house. Yeah. The house has been under construction for like months. The kids help out. No, it's a different house. All right. Which sets are bases for R2 or R3? Okay, this one. All right, so when they only give you two vectors, it's pretty nice because you can just check if they're scalar multiples of each other, and they're not. So therefore, this is a basis for R2. Whereas this one, you multiply this by -2. The span of this is only one dimensional. You can't get everywhere in R2 from that. I'm not doing the 3s. That's too much work. This one spans it spans a two-dimensional subspace of R3. So no, it's not a basis for R3. All right, true false. True falses are good. Whoa, look at this. Bug. They wrote tour. They wrote tour instead of false. How did that even make it through this quality control? One, you really makes you think. Are they putting any effort into this thing at all? All right. A subspace of Rn is any set H such that the zero vectors in H So the reason why I'm going to say that this one is false is because it doesn't anywhere specify that the elements of H are in Rn. So if they were to get rid of Rn, then a subspace is any set H such that the zero vectors in H and in, whatever. So I'm going to put false on that one. They always try to trick you on these true false ones. So this is false. 22 is a subset H of Rn is a subspace. Again, this is false, obviously. Just obviously false because it needs closure under addition and scalar multiplication. All right, if V1 through Vp are in Rn, then span of V1 to Vp is the same as the column space of the matrix. That is true. Given vectors in Rn, the set of all linear combinations of these vectors is a subspace. That's true. The set of all solutions of a system of M homogeneous equations in N unknowns is a subspace of Rm. That's true. You got to think of it's an M by N matrix, so its domain is going to be Rn, and its codomain is going to be R. Wait, yeah, it's going to be Rm. The null space of an M by N matrix is a subspace of Rn. That is also true. 26 is true. 27, the columns of an invertible matrix form a basis for Rn. That's true. And it's because the invertible matrix theorem, those are independent. And any set of n independent, any set of n independent vectors is going to be a basis for Rn. Okay. The column space of matrix A is the set of solutions. I don't really know what they mean here. I would say yes. If it's the column space of matrix A is the set of, well, solutions would be the values of X. So no, that's wrong. That's false. It would be the set of B is such that AX equal to B for some X. Because that would represent all possible linear combinations of the columns. So this is false, but it's like a trick one because it's close. 29, row operations do not affect linear dependence relations among the columns. That's true. That's true. Row operations do not affect linear dependence relations among the columns of a matrix. Yeah, that's true. All right, 30. If B is an echelon form of matrix A, then the pivot columns of B form a basis for column. No, that's wrong. That's false. All right, now we're just going to ask ChatGPT to verify all of our answers. Okay, so what did we get? Wait, 21. 21 they gave true, but I'm taking issue with ChatGPT's answer. I don't think that's right at all because it doesn't ever say that H is a subset of Rn. So I think I'm right. Okay, anyways, we're going to move on. 22 is false. Is necessary but not sufficient. That's true. 23 true. 24 true. 25, they said 25 is false. The set of all solutions of a system. Wait, so we have an M by N matrix. And we're saying the solutions an equation assumes that there's a B. So we have a B. So X is in Rn. So the set of solutions of that oh, that's right. I got tripped up. That one's actually, yeah. 25 is false. It's not Rm. The set of solutions, meaning the values of X, is going to be the number of variables. So that is that's Rn. That's true. All right. Wait, did it say homogeneous? Oh yeah, it's homogeneous. That means the B is 0. But yeah, it doesn't change anything. Okay, cool. 26 is true. Which I got. Okay, 27 is true. 28 is false. What was the question again? 28 was the column space is the set of solutions, but it's not. Yeah. And then 29 is true, and then 30 is false. All right, so we got all those right. Let's see, how long have we been going? Almost 1 hour. Display a matrix A in an echelon form of A. Find a B. I don't want to do that. That's so boring. It's literally just row reduce it. Construct a non-zero 3x3 matrix A and a non-zero vector B, such that B is in the call. Um, is one C dot plus I, where C and R and I, the identity, always independent. I'm pretty sure that it is. Great. Wait, in particular. Oh. Okay. Okay, but if I add one, so if I do, the matrix 1 plus I, then I'm going to get 2, 1, 1. Wait, did it say 3x3? Yeah. Then 1, 2, 1, then 1, 1, 2. So this is my A. So if A is, let's say, how do I do I of 3? Can I do this? Does this work? Okay, cool. So if I do 1 plus, I have to broadcast it, I think. All right, so if I get this, surely this is invertible. But the point is construct a non-zero matrix A and construct a vector B that is not in. Oh, you know what we could do? So we need. Oh, this is a good problem because you need to find. Oh, God. You need to find. You need to make A so that it's dependent, so that it doesn't span R3. And then you make B something that can't be hit. I'm just gonna get the answer to this one. I think as long as you see the answer to this one, you don't really need to come up with it. So anyway, something that's independent is not gonna be good because you're trying to. It said non-zero though. Oh, but you know what? Non-zero in this context. Okay, yeah. So that's the best one. That's what I was thinking. But I for some reason I was thinking that non-zero meant all entries non-zero, but it just means that no entries that some entry has to be non-zero. Uh, construct a non-zero 3x3 and a non-zero vector B that is in the null space. Okay, we'll do this one. 37 is. Let's just do a 2x. Let's just do a 2x2. If we do 1 minus 1 0 1, and we multiply this by 1 0, we're gonna get. Is that independent though? If we do A is equal to 1 minus 1 minus 1 1. Oh, so this is not independent. Oh yeah, obviously it's not independent. What am I talking about? All right, I say we just go for it. I mean, these ones, it's just like, just reinforce it, you know. Oh yeah, I don't know why didn't realize that. It's literally the same one. Yeah, so this is a great example. Actually, is 1 0 0 0 1 0 0 0 0 times 0 0 1. In this case, this is A and this is B. Then B is not in call A and B is in null A. All right, so that's actually a really good example. It's like the value of the projection matrices. It's just like, all right, let's keep going because we're just blazing through this. We only have 5 left. Respond as comprehensively as possible. Suppose F is 5 by 5 whose column space is not equal to R5. What can you say about the null space? All right, they're just trying to tell you that the dimension of the null space plus the dimension of the column space. Yeah. Yeah, you can go to that. Yeah. Okay, so basically they're just trying to get you to understand the rank theorem. It's like the dimension of the column space, which is defined as the rank. The rank plus the dimension of the kernel or the null space is going to be equal to, well, what if it's not square? Oh, then you get the inequalities. But if it's square, then it's going to be 5. All right, so we're going to double check these, but I'm going to write them down just so that we can. Okay, so they're just trying to say that the dim of call A plus dim of null A is equal to 5. With them both being great. I mean, you can't have a negative dimension. If R is 6 by 6 and null R is not the 0 subspace, what can you say about call R? It doesn't span R6. 41. If Q is 4 by 4 and the, what can you say about the solutions? Oh, you can say that they're unique. First off, you can say for all B they exist and they're unique. So they exist and are unique. So what am I trying to say? I'm trying to say for all B, X, a unique X exists. Okay, great. 42. If P is 5 by 5 and the null space is the 0 subspace, what can you say about solutions of equations of the form? How is this different? I feel like this is the exact same. Okay, 42. If null B equal to the 0 vector, then the call B is equal to R. What did we say? 5? Or wait, is it? Oh, it's P. Whatever. I said B. It's P. Then so then we have exists unique X for all B. Great. So it's the same thing. What can you say about null B when B is 5 by 4 with linearly independent columns? You have four you have four vectors of length 5 and the 4 are independent. What can you say? I mean, clearly they don't span R5. How could they? I would say what they are is that the vectors generate a 4-dimensional. Unfortunately, the book hasn't defined dimension yet, but I think we all know what's going on. It's not that hard. Generate a 4-dimensional subspace of R5. And then, what can you say about the shape of an m by n matrix A when the columns of A form a basis for Rm? I think what they just want us to say is that n must be greater than or equal to m. All right, we are just going to copy all of these and verify our answers. I bet this word comprehensive makes it write a freaking essay on each of these things. Oh no, good. Being succinct. Yes. Okay, so that's exactly what I wrote. The dimension of the column space plus the dimension of the null space is equal to 5. What? Why is it doing this? All right, I don't care. We can read it, but I want to see if it can fix itself. Because that would be pretty cool. It's not supposed to look like that, buddy. All right, I don't care. Okay, 40 is, it doesn't span R6. Is a proper subset, or subspace. Perfect. Okay, they exist and are unique. For every B, there's exactly one. Perfect. That's exactly what I said. 42. If it's invertible, then we have a unique, exact same thing. Nice. Wait. One sec. What's up? All right. So what did I say for 43? 43, I think I did a little bit weird. So 43 was, what can you say about null B? Oh, so I didn't say anything about null B. Okay, so the true thing is that for this one, null B is equal to the 0 vector. So even if wait. Yeah, that's true. So even though there's 5 equations and there's no way we could span R5, since we know that the columns are independent, then independent columns means that the only vector that's going to send it to 0, that the linear combination to 0, is the 0 vector. Great. And then number 44. It didn't say anything about their independent. Oh, wait. What did it say? Oh, wait. This is wrong. Since they specifically said calls are a basis, implies independent. Therefore, n is equal to m. Okay, cool. And then the rest are just like, these two are just, boring. All right, so we were able to get through this pretty fast. 1 hour to get through subspaces in Rn.